Alrighty, why don't we make a start here? Good evening, everyone. Good evening, and a very warm welcome to Green College and to the Resident Members Series. My name is Nico, and I have the honor and privilege of being one of the chairs of the Resident Members Series this year with Aaron. We'd like to start off by acknowledging the lands that we're on, traditional, ancestral, and unceded territories of the Musqueam people, and that this land has always been a place of learning far beyond Green College and UBC being established. For those who are new or maybe perhaps watching online, a very warm welcome to you. The Resident Member Series is an opportunity for resident members to provide talks on things around their research or topics that they find interesting here every Monday night in the Coach House, as well as to you all, the public through Zoom. It's a real delight to have Rishi with us tonight. Rishi is a master's student in the Department of Physics and Astronomy. We're really excited for his talk entitled, "So What is Quantum Anyway?" Following Rishi's talk, we'll open up the floor for Q&A. And so please do feel free to leave your questions to the end. And if you have any questions on Zoom, we'll attend to them as well after Rishi's presentation. So without further ado, please do welcome Rishi to the floor.
Okay, thanks, Nico, for the introduction, and thanks for the land acknowledgement. Spent over 5 years here and sort of in this beautiful place, learning and making friends. So I'm immensely grateful for the hospitality of the indigenous people who the land belongs to them, right? So this talk, I've divided it into 3 parts. The first part is sort of covering the basics of quantum. So it will be like a refresher course. So if I go through part 1, it's 3 parts, but if I in the hour that I've been allotted, if I finish the part 1, I've delivered. Okay, but it would be nice to go through all the 3 parts. But before we start talking about quantum, here's a landscape for you. If I can get this part. Okay, I guess I have to stay here. So physics or physicists like to divide everything in 4 quadrants, hot and cold and big and small, right? And physicists like to stay at the corners of this. So anything in the middle that's humans for comparison, that's what we call engineers, right? So we like very hot stuff, we like very cold stuff, we like very big stuff, and we like very small stuff, right? So some examples are like if you're into very cold and big stuff, that's galaxies, dark matter. Riku, Pedro, they all sort of work on this. Then there's particle physics, which is hot, so somewhat hot at least, and small. So there's few people who kind of work on that. I'll be in the southwest corner here. So I'll be in this corner where we have cold stuff. So I'll be talking about small stuff, so like atoms and electrons, that sort of thing. But they're cold; they're not hot. So when they're hot, they're that's a different kind of works. Okay. Okay. So the first part is sort of everything that was done pretty much more or less before 1930s. And the blue part, okay, just going to use this. So that's part 1, brief history of origins of quantum physics, just part 1. Second part is going to be using quantum physics to make devices or sort of applying quantum physics to real world problems. I wanted to keep this as the 3rd section, but I promised this in my abstract, I realized. So I was like, okay, I have to refer to part 2. And part 3 is something that I'm very interested in, and that's the middle part. So there's a gap of 50 years between the green and the blue part, and that's where the red part comes in, and that's about emergence. So quantum physics is like such an interesting science, but it is only really applicable to sort of small stuff, atoms and electrons and whatever. So asking ourselves, why would this be at all useful for real world objects? And that's where the third part comes in. So there's the idea of emergence of sort of objects that can use quantum physics. They can be quantum mechanical even at a macroscopic scale. Let's say that. Okay. Okay, so before we go to quantum, we have to start with classical physics, which is somewhat boring, but let's do that. So physics pretty much started with Sir Isaac Newton. In 1600s, he came up with the law of gravitation. You know, any two objects which have mass, they experience an attraction due to gravity, and that attraction is proportional to the masses of the object, and it's inversely proportional to the distance squared. And by the way, this slide is probably the only slide where you have any equations, which is, I don't think you'll find another physics talk with that. Then came along Coulomb, and he said, okay, if we have two charges, the force between those charges is actually also proportional to the two charges, and it's also inversely proportional to the distance of the two charges. And this was 1700s. And then came Maxwell. So this is sort of the end of classical physics now. This is late 1800s. Maxwell came along and he said, okay, so Mr. Coulomb gave us a law that says, okay, the force between two charges is given by this law. And once you have force, you can basically determine the dynamics of any object, right? So you can predict deterministically where the object will go once you know the force is acting on an object, right? And Maxwell said, okay, so that's right, Coulomb was right, but there's also this thing called electric field. So every charge can have an electric field associated with it. And any moving charge can create a magnetic field. And essentially, these electric and magnetic fields pair up together to make light, right? If this sounds confusing, you won't see this again. The rest of the talk, because this is about quantum physics, not classical physics, right? Maxwell was right, but in late 18, after this discovery, I think this was late 1800s. So people thought, okay, physics is solved. They were not taking any graduate students in physics anymore, right? It was like, okay, nothing to do here. But then people started doing experiments, sort of, the reductionist in scientists, they always want to break things down and ask, okay, what's this made of? If you have this piece of glass, you break it, and then you say, oh, it's made of silica. What is silica made of? Silicon and oxygen. What's silicon and oxygen made of, right? So you can keep going. So people were doing this in late 1800s and 1900s, and they realized that there were two problems with this. First was the problem of, or I don't know which one came first. I think probably the second one, but okay. There were two problems. One was that of spiraling electrons. So if you have, think of a picture of an atom, right? So you might have seen a picture of an atom in a high school textbook where, there's a nucleus, positively charged nucleus, and then there's electrons orbiting around. There's a problem with that picture, and that is that electrons have charge, and an orbiting electron would lose energy because according to our friend Maxwell, moving electron emits light, and that light, basically, it's losing energy as it's going. And that means that as it orbits the nucleus, it will spiral into the nucleus, meaning that the atom is unstable. But that's not what we see. Here's an atom. It's not unstable, right? It's made up of atoms, it's not an atom. But so there was clearly something wrong with that picture. It's not like a solar system where it's in the center and then there's orbits. There could be orbits, but something more is needed. That was the idea. Another problem was that of black body radiation. So think of an object that's kind of a perfect emitter and perfect absorber of light. It's kind of hard to imagine that, but let's say there is some object, and objects do exist that are close to that are sort of very good at emitting and absorbing radiation. And the theoretical predictions at that time showed that these objects at the UV length scale, so these objects can emit radiation. Radiation basically means light. Okay. And basically, if it emits a microwave or radio wave, then it's fine. Infrared is fine, visible is fine. But if an object radiates ultraviolet rays, then the prediction of theory, the Rayleigh-Jeans law, said that the energy emitted should be infinite. And again, there are many sources of UV light. The sun emits UV light, and it doesn't emit infinite light, right? It's infinite energy, right? So that was a problem with the theoretical prediction. Experimentalists were sort of measuring this, and they were like, yeah, that's not true. This was the experimental curve, and this was the theoretical curve. So we needed a theory that was consistent with these observations. Physics is always informed by what we see out in the nature, right? So we wanted to explain these things. This was, circa 1900, probably late 1800s. Okay, so on comes Max Planck, and he gave a resolution. So he came up with an idea that actually light is not a continuous wave. It's actually made up of particles. So it's quantized. That's what he called it. A quanta means a packet, and that's where the word comes from. And what we will discuss later in this talk, this is kind of a misnomer, because I mean this idea of quanta is in some sense important, but it's, as you go higher in scale, it's kind of irrelevant. But nonetheless, this was the idea that that seemed to fix the problems that were happening in the black body radiation. So Max Planck was trying to answer the second question, that the question of black body radiation, of the ultraviolet catastrophe, because theory was predicting infinite radiation. And he was able to answer that. He was able to match the experimental results using this assumption. So simply, if you remove the assumption that light is a wave and replace it by the assumption that light is a particle, it's made up of particles, then it works. And similarly for the spiraling electron, if you assumed certain orbits, so not all the orbits were allowed, but think of a loose analogy, but think of certain energies that are sort of resonant with the atom, right? So there are certain energies that are favorable because of the intrinsic structure of the atom. And in that case, if you restricted the electrons to those orbits, then you no longer had the problem of spiraling electrons. So the electrons were in fixed orbit, and everything was fine. So, and this was also verified by experiment, and this was a famous emission line spectra, which basically says if you have a hydrogen atom and if you shine a bunch of light, the electrons would excite and then release these very specific lights. So you would only get this wavelength, and not like you can't get an entire spectrum of light from hydrogen. You can only get certain specific lights, and that was kind of a proof that these levels are quantized. There can't be any orbits, but they have to be fixed by some intrinsic symmetry of the system. There was also an experiment in early 1800s, actually. So this is actually much before Maxwell and Coulomb. In fact, this was the Thomas Young's double slit experiment. And this concretely proved that actually electrons or light, it's a wave. They showed that it has to be a wave. So if you have a wall, if you make two holes into the wall, and if you pass light into it, then the pattern that you see on a screen that's sort of at some distance away from these two holes is this interference pattern. So you see these fringes. And the only way you can get these fringes is if you have this sort of interference. So think of these as water waves. If this is just two particles, and as they go along in the along these two poles, you would only have two bright spots on the screen, right? That's what a particle would create. But if you send a wave, then you create these interference fringes, and that's what he saw. So this was saying that, okay, electrons and basically quantum particles are waves, but then the previous slide said that they are particles, right? So that's clearly, if I spill this, that would create a wave. That's a wave, not a particle. So particle and waves are not the same thing, but in the world of quantum, they are. So when we say electron is a wave, think of electron as an assuming traveler, and the probability of you finding that traveler somewhere is given by this wave. So if the wave is cresting here, that means that the electron is there. If the wave is cresting here, then that means that the electron is there. But that also means that the electron could be here, but there's also a small probability that it could be here, right? So waves, when you ask what's the location of the wave, that's a stupid question, right? Because waves are everywhere, right? Like waves are not localized objects. They're everywhere. So you can't ask with location. What you can ask is the probability of finding the electron at a certain location from this wave. So when I say electron is traveling, what I mean is that this wave is traveling, and the crest of the wave will tell me what are my chances of actually finding the electron. Okay, so that answers the question of, okay, it's a wave. What about particle? So this is maybe the most baffling part of quantum mechanics, and this Einstein could never get over this. So he was one of the founders of quantum physics, but this idea was perhaps the most difficult to digest. And that is that if you have this wave of electron, and if you want to measure this electron, so if you have a normal wave, you can just see and you can say, oh, the wave is there, electron must be there. But in quantum physics, you can't really do that. You have to actually disturb the system somehow. So when you are asking the system, where are you? You have to do something to the system to actually know where it is, right? So you have to do some operation, and then the operation will tell you, oh, the electron is here or it's not here, right? In doing this operation, you collapse this wave picture. So this wave picture no longer holds. What happens is that this wave turns into just a single peak. And this is a particle, right? You can say, okay, the particle is here. It's not a wave, it's here, right? So if you find a particle at this location, it turns into this. So measuring something in classical physics is easy. You just look at it. Measuring something in quantum physics is an active, it's an active process. When you measure something, when you ask the system what state you're in, or where are you, or whatever question you want to know about the system, you are changing the system by, that's just how it works, unfortunately. I say unfortunately because then now you've destroyed this wave, right? So initial state of the system is gone. Now it's just this. And one more note. The fact that it's a wave also means that you can think of the idea of superposition, which I'll describe in a second. Okay, I think I already mentioned this, but yeah, waves can be here and there, particles cannot be here and there. And this is an actual simulation of sort of an electron oscillating between 2 points, right? So there could be a wave, it's here, then it goes here and here, back and forth, back and forth. Okay, so again, balls can spin clockwise or counterclockwise, not both. But electrons can spin clockwise and counterclockwise, right? And this is where the idea of superposition comes in, right? So you can have a state that is contradictory, but it can be in contradictory states at the same time. And this is because of the wave nature of the electron. It can be here and there. In the same sense, electrons can be up and down at the same time. And there was this famous thought experiment by Schrodinger called Schrodinger's cat. If you haven't heard about it, it's a simple thought experiment. Imagine a cat in a box, and there's a poison chamber, and there's a 50% chance that this hammer breaks this poison, and it will kill the cat, right? But imagine that this cat is somehow quantum. Cats are not quantum, but imagine. If that was the case, then the cat is in a superposition of dead and alive. So it's both dead and alive at the same time. But when you measure it, so when you open the box, then you force the system to make a choice. So when you open the box, you ask the system, is it dead or is it alive? And with a 50% chance, it will be dead or alive. In some sense, you kill the cat, but not really. So if this doesn't make sense, that was kind of the idea, that you can't apply quantum mechanics to cats. But this is what actually happens in our quantum universe. Okay, I guess I delivered. So we are on to part 2, quantum real world. Okay, so part of my research is on sort of making quantum, or like designing quantum computers. I don't make them, I'm a theorist. But a good question to ask ourselves is, how can we make a computer out of this quantum business? And there is a way, but before that, I'll have to explain to you how computers work. This is kind of a simplistic analogy. So if anyone here is in computer science, you might be offended, sorry. So classical computers are essentially made up of switches, right? So they are made up of transistors, and what transistors do are they either have an on state or an off state. There's billions of transistors in your computer, but the way they process information is that the computers process information in binary, right? So they're turning these switches on and off super fast to process information in your computer, do computations. For example, this word here, cat, you can write this word in language of computers, binary, in terms of the switches, right? So our English language has 26 alphabet, right? But computers only have 2 zeros and ones. You can, it's a perfect system, so you can translate any word in English to a binary, right? So it's just a different language. A simple word cat needs 24 bits to represent in a computer, right? So you need 24 of these arrows. Down arrow means 0, up arrow means 1, right? And in this representation, so in this English, you only need like 3 bits, 3 characters, but in binary, you need 24. And the idea here is that these 24 bits can have, if I give you a set of 24 bits, there can be 2 to the 24 combinations. So by 2 to the 24, I mean 2 times 2 times 2 times 2 times 2 times 2, 24 times, right? Why? Because this first bit can be 0 or 1. So there's two possibilities. The second one can be 0 or 1. So there's 2 times 2, 4 possibilities. Third one can be 0 or 1. That's 2 times 2 times 2. That's 8 possibilities, and so on. So if you have 24, 2 to the 24 configurations. And this is just one of the configurations of the 2 to the 24 that you can have in total. In quantum, you can represent all the 2 to the 24 configurations all at the same time. So this is one. So cat alive or dead. So cat dead is a configuration. Cat alive is one configuration. Cat dead is another configuration. In quantum, you can have a superposition of these configurations. So you can superpose all these configurations in a single state. And this allows for computational speed up because when you can just have one qubit that can, or if you have 24 bits, just like classical bits, then you can only access one of the states of this entire space of possibilities. But if you have 24 qubits, then you can access all of the 2 to the 24 configurations. And that's where if you're, these are details, but if you care about doing computations in parallel, these can be super good. And most of the algorithms that people have designed for quantum computers are made to exploit this idea of superposition. Superposition is the big idea that quantum uses to speed up certain problem solves, solving certain problems. And the cornerstone example that's given is the Shor's factoring algorithm. And this was kind of, so the idea of quantum computing was first popularized by Richard Feynman in, I think, it was 1980s or 70s in one of his essays. And people didn't really know sort of what applications it could have or if there was any known advantage to that paradigm of quantum computers. But this was one of the first sort of real world algorithms. Shor's factoring algorithm is an algorithm to factor large or factor prime numbers. So prime numbers are essentially, 2, 3, 5, 7, 11 numbers that only have two factors, the number itself and 1, right? So 2 has factor of 2 and 1, 5 has factor of 5 and 1. But if you pick 6, 6 has factors 2 and 3. So that's not a prime number. So 6 is not a prime, right? So so for these small numbers, if I give you 6, then it's easy to factor, right? You just know 2 and 3. But if I give you some huge number, like 10,565,000, and if I ask you, is this 67, let's say, if I ask, is this, what are the factors of this number? Is this factorizable? And if so, can you give me factors? This is a very difficult task. You basically have to go through all the numbers leading up to that number almost to determine if it has any factors. So for example, if you have the number 10, you go all the way up to 10, right? So you say, okay, 1 is a factor, 2 is a factor, 3 is a factor, 3 is not a factor, 4 is not a factor, 5 is a factor, 6 is not, 7, not 8, right? So you have to go all the way up to 10. Not all the way, but like after a point, you don't have to. But the idea is that if I give you a large prime number, that is going to be excruciatingly difficult to factor brute force, right? So you have to just go through all the combinations and ask yourself, is this factorizable? And so a lot of the encryption that you see nowadays, so when you make a bank transaction, for example, it's based on this hardness of the factoring problem. Factoring large numbers is difficult computationally, so what they do is they make a key, which is basically 2 big numbers, 2 big prime numbers, and they multiply it together. So this is a problem where you can check that, okay, these are to the factor. If I give you 2 numbers, you can check if those 2 numbers are the factors of that big number, but you can't figure them out brute force. Let me repeat, that's not clear. If I give you if I give you a big number and if I give you its factors, you can check if those are the factors pretty easily. You can just divide and see if it factors, but you can't find those factors easily by yourself if I didn't give it to you, right? And that's why this is used in encryption protocols. Shor's algorithm is an example of an algorithm where you can do this fast or efficiently is the word that they use. Compared to the brute force approach, this Shor's algorithm will be exponentially faster in factoring numbers and finding the factors essentially. So this could, in principle, break your RSA encryption. You could become a billionaire, if not a trillionaire, if you figure out how to make a quantum computer first and then implement this algorithm. So you already have the algorithm, you can look it up. But I guess the big question right now is, how do you even make a quantum computer that would allow you to do this? And that's the hard part right now, because as I sort of prefaced, quantum computers, they like quantum is restricted to the realms of electrons and atoms and whatever. It's hard to make a computer, a macroscopic object out of it, right? I will describe a way that people have been building it, but it has some serious challenges, and that's one of the reasons why we don't have a good quantum computer. That's one of the reasons why RSA is still very secure. There are ways. So once we figure out the quantum computer business, we already have algorithms that are resistant to this attack. So you don't have to worry about, if someone makes a quantum computer, you don't have to be, oh, shoot, I'm going to be poor. And just to sort of give you a sense of scale, the RSA key has 2048 bits. So the size of the number that your computer would have to factor would be 10 to the 616. So that's 616 digits approximately. So that's a huge number to factor. And if you don't have, that would be almost impossible to brute force. You can't brute force that. So you need efficient factoring algorithm if you even hope to break RSA. Okay, so one of the ways you can realize this quantum computer is using a supercomputer. And why? This will be sort of what I'll cover in part 3, but supercomputers are these really amazing objects that are macroscopic, but they are by definition, almost by definition, quantum. Superconductivity, let me first describe what it is. Superconductivity is basically if you take a piece of aluminum or some other material that has some similar properties, it is when you cool it down to a certain temperature, its resistivity drops. So what I mean by that is that if you have a normal metal, let's say iron, if you cool it down, its resistivity will decrease, but it will not be zero. So as you pass current through the system, it will, I'm not sure if you might be familiar with Ohm's law of some electrical devices, where if you pass some voltage, if you pass some current, it faces some resistance. But the superconductor is some really amazing voodoo magic device that when you drop the temperature of the system below a certain critical temperature, doesn't matter what that is, the resistivity is exactly zero. And this was discovered this phenomena was experimentally discovered in 1911 by a Dutch physicist called Camille Ons. But we didn't have an explanation for this until late 1950s. So for a good 50 years, we had this object, but we didn't know what the heck it was or like how it worked. And the reason is simple, and that's we had quantum mechanics by 1930s and 1940s, but this is a macroscopic object. This doesn't just have a bunch of electrons flying together. This is some completely new thing that is quantum, but the laws are different or they're modified. And using this sort of purely quantum device, so you can't explain this using classical laws. If I gave you the Newton's, Maxwell, and Coulomb laws, this is impossible to describe using those laws. You need a very, very quantum treatment to theoretically explain this phenomena. But if we can do that, and I'll talk about this in briefly, so I'm just advertising that right now. But if we can utilize this, then these are details, but you can make a sandwich of these aluminum superconductors, and that's called a Josephson junction. Details, but that junction has properties that can be used, that has the superposition property when you pull it down, that can be used to make a quantum computer. And people have made this already. So this is, if you have heard, IBM, Google, the big tech companies which are making quantum computers, they use this set of superconductors. And this is an actual picture of the IBM Falcon quantum computer. And this huge thing that you see is actually, that's not the quantum computer. That's the fridge. that's the thing that keeps it cool. The quantum computer is right here. That's the superconductor right there. Okay. I have not described to you how this works, but I think the reason I decided to skip this is because it's detailed and I don't think it's very enlightening. What I want to focus is the idea of how this huge object can be considered quantum, or why is it even quantum, right? That's the question we can ask. And that brings me to the third part, which is emergence, the idea of emergence. And this was popular. I don't think, this is Philip Anderson. He Nobel laureate physicist from 1970s, and he worked on a lot of these problems. And the idea of emergence, which I'll describe, is an idea of complexity. So as you have some system, and as you get more and more and more complex, you have to understand that the laws change, right? So for example, if I can't explain politics with the laws of particle physics, right? Politics is so much more complicated than particle physics, right? So this idea of emergence comes from that sort of general principle, but he popularized it in the physics community because I think the idea of reductionism is, it's up for debate in the philosophy department, but a vast majority of scientists still use reductionism as their working philosophy. If you don't understand something, you break it down, and then you investigate the pieces, right? And that works. That is correct. But there's a fallacy to that, and this fallacy was pointed out by Philip Anderson, and that is people assume constructionism. People assume that once you understand the parts of the system, once you understand the fundamental laws of physics, then you can understand anything. That's not true. And that's what he pointed out in his really nice essay called More is Different. I recommend you checking it out. It was amazing. So it's important that we understand this, that laws of physics are, or laws of any sciences, they differ as you go up in system size or complexity. Just for scale, you can start with, this is called the standard model of physics. This is considered the building block of physics. There is 17 particles here, and a lot of physicists agree that this entire universe is pretty much made up of these. There could be one more, but this list is almost complete. So given this idea that this list is almost complete, an arrogant physicist should think, this list is almost complete, we should understand almost everything there is to understand in physics. But that's where the fallacy of constructionism comes in, right? You just can't, right? Based on this, it's hard to go directly, okay, from here to here you can go, but then here, all the way here, that's a stretch, right? So then sort of, how do we proceed, right? And the way we proceed is by investigating broken symmetries. And what do I mean by that? So imagine yourself on the top of a hill, and you can imagine that this hill is completely symmetric, like this picture. So you're on top, right? So in that scenario, you are in a very symmetric case. You are equally likely to fall in any of the direction. Right? So this, if you're here from that point of view, spaces, everything you see around yourself is isotropic. Everything is nice and symmetric. But once you fall from this hill, you can fall in any direction because this is sort of it's symmetric in all sides. Once you fall, then you've broken that symmetry. You're broken. Now the space is not the same everywhere. And this is the idea of breaking symmetry. This is pretty abstract. So let me give you an example. So this example I borrow from Philip Anderson. So think of the ammonia molecule. And ammonia is nitrogen, and then there's 3 hydrogens that are sort of paired. So it looks like a pyramid. So there's a nitrogen on top, and then there's ammonia, and then there's hydrogen in the bottom. Now, if you know a little bit of chemistry, there would be a dipole moment here because nitrogen is negatively charged, or it's polarized, so it's negatively charged, and hydrogen is positively charged. So there will be a net dipole moment pointing up. But when you take a piece of ammonia, that doesn't like if I put charge on it, there's no force, right? So ammonia is if I just take this, like if there was ammonia here, that's not like that's probably neutral. It doesn't have charge. Where does this dipole moment go? So in the case of ammonia, what happens is that because nitrogen is pretty light, and hydrogen is also pretty light. What happens is that this nitrogen flips and goes down. So it goes here and then goes back up. So it oscillates between these hydrogens. So these hydrogens make a plane, they make a triangle, and the nitrogen sort of goes up and down. And this happens at a very fast time scale. So this happens like 10 to the 10 times in a second, right? So this is super fast. So you would not see it if you put a camera, right? And that means that because when it does that, it's canceling out the dipole moment, right? It's like half the time it's here, half the time it's here. So there's no dipole moment. That's why. This is a crude analogy, but that's the basic idea, right? But if you go up in scale, think of a sugar molecule. Sugar is very heavy compared to ammonia. It can't do that. It can't oscillate like that. This process is called inversion. It can't do that. So what happens is that it breaks this symmetry. It chooses an up orientation, or you can say right or left. And nature is obviously very symmetric. So when you take a bunch of sugar, half of it is pointing up, half of it is pointing down. But each of the molecules have broken the symmetry. So if you look at the molecular scale, the symmetry is broken. And this is important to understand for many body physics. Because the sugar molecule does not behave like ammonia, right? So if you just started with ammonia and then you try to apply the symmetries of ammonia to sugar, it doesn't apply. The ammonia molecule has the parity symmetry. Parity basically means that this inversion happens so fast that it's essentially neutral. It doesn't have a dipole. But it doesn't work in the sugar case. So you always have to ask yourself which symmetries are broken when you go up in scale. And this is what happens in the case of superconductivity. And this is why superconductivity is so, it took like 50 years to understand, and it's so interesting, in my opinion. But if you take a piece of aluminum, just at room temperature, the electrons in aluminum are just randomly bouncing off each other, right? There's no order to the system. But when you cool down the system, to negative 272 degrees, very cold. But if you can do that, then somehow, just somehow, this symmetry, this is it's kind of hard to picture, but this is the symmetric case. Every electron can go in basically any direction, right? So it's kind of symmetric in that sense. There's no, the absence of order is symmetric because it doesn't have a preferential choice, or it doesn't have a preference for a configuration. But when you cool down aluminum to this temperature, electrons make pairs, and those are called Cooper pairs, named after Leon Cooper, who discovered this. And these pairs are then so well maintained, or sort of, so they behave so nicely that these pairs conduct electricity. So that's why it becomes superconducting. This, like, if you think of an electron going through this random mess, it faces resistance as it passes through, right? But these somehow, we understand how, but I'm not describing. When you cool it down, these electrons make a pair, and those pairs work they just work flawlessly. They just move along in a non-resistive fashion. And this is even more surprising because electrons are both negatively charged particles. So if you think Coulomb's law, they should repel each other. They absolutely should repel each other. So that's why it took 50 years, because people were like, no way electrons can form a pair, right? It's just impossible. But there are cases where they can form a pair. There can be attractive interaction between electrons. And that's essentially because of the symmetry breaking idea. There's a lot of math that went into it to sort of prove that this is actually what happens. If you're curious, you can look up. There's a really nice history behind this theory called the Bardeen-Cooper-Schrieffer theory. So Bardeen was the PI of the lab. Cooper was a grad student, and Schrieffer was a postdoc. This was Bardeen's second Nobel Prize. First one was for transistors. But some really interesting history behind this, because this was kind of the holy grail. People were blown away as soon as this was sort of put forward. A lot of the 20th century had so many sort of amazing scientists, amazing physicists, like the list goes on, Einstein, Planck, whatever. But it was a graduate student who figured it out. So. Okay, this is my last slide. New laws and generalizations occur at every complexity. This is the main idea that I'm passing along, right? So I think most of us sort of maybe back in the head, like they think, yeah, of course, this is kind of obvious. Like constructionism doesn't work. You can't apply laws of physics to politics or physiology, even, right? But we sometimes make the mistake of where do you draw the line? Like, at what point do laws of physics can't apply, right? So people thought that superconductivity could be explained just from brute force, quantum physics, and they didn't think of sort of pairing electrons, right? So where do you draw the line? Okay, after this point, you can't apply directly the laws of physics, or it's not possible. So yeah, I just want to sort of ask all scientists to be cautious when you're we all know it doesn't work, but sometimes we all make the mistake of assuming constructionism. You always want to build from some building blocks. There's some problems with that, and superconductors are smoking gun evidence of that, of why that might happen. Right? And the way forward is sort of asking ourselves, what are the symmetries of the system, and what symmetries can be broken as you move along in scale and complexity. As you increase complexity, which ones can be broken? And once you understand this, then I think problems. You can look at problems from a different lens. And this is a question, I don't know the answer to this question, but a question for you to think about. I think in all of the research, there is always some scale involved. You're whatever you're doing, you can always say, I'm talking about only this thing, or I'm talking about the entire, entire group. And can you generalize this, robustly generalize this idea of symmetry breaking outside of physical sciences? I have not thought about it, but if you would like to talk about it, I would be super interested in discussing this. Anderson, in his essay, does point out some things beyond physical sciences. I don't agree with a lot of it, but yeah, would love to hear what you have to say. And yeah, I would like to give special thanks to a postdoc in our group, others. He was the one who sort of pointed out Anderson's essay to me, and some of the ideas that I present today are sort of inspired from conversations with him. So